Hello everybody, welcome to the solutions to Superquiz 2. We are in fall 2022 Math 350, that is Advanced Calculus 1, known to the rest of the world as real analysis. All right, our first couple problems have to do with the basics of set theory. And in our first one, we're going to prove that the complement of the union of two sets equals the intersection of the complement of the two sets. So rephrased here, you can see, right, you have two sets S and T. I want to show if I take the union of S and T and then take the complement, it's the same thing as if I intersect the complements of S and T individually. All right, well, we're going to do kind of a slick proof of this. Typically, though, let's just mention when you're trying to show that two sets are equal, right? So if I want to show A is equal to B, where here A and B are sets, then what I'm required to do is to show that A and B have the same elements. And so one way of doing that is by saying, well, let me show A is contained in B and B is contained in A. Right? And when I say contained, I mean is a subset of. And what does it mean to be a subset? Well, it means every element of A is an element of B, and every element of B is an element of A. So this is equivalent to showing X is in A implies X is in B, and B subset of A is equivalent to showing that X is in B implies X is in A. So when we get down to this level of elements, it becomes clear what we need to do. I need to start with some element of the complement of S union T and show that it also is an element of the intersection of the complements, and then vice versa. And I said we're going to do it kind of in a slick way because I'm going to do both directions at once, essentially. All right, so let's consider if I had X in the complement of S union T. Well, what would that mean? That would mean that X is not in S union T. And that's an equivalence, all right? If X is not in the union of S union T, that means it's in the complement of S union T. Okay, well, what does it mean that X is not in S union T? Well, things in S union T are things that are in S or in T. So if I'm not in the union, then I'm not in either one of them. So this is equivalent to saying that X is not in S and X is not in T. Okay, you read it backward. If X is not in S and X is not in T, then yes, X can't be in the union. But what does it mean that X is not in S? That means that X is in the complement. And if X is not in T, then X is in the complement of T. Of course, that's again an equivalence. This is equivalent to saying X is in the complement of S and X is in the complement of T. If X is in the complement of S, then it's not in S. If it's in the complement of T, then it's not in T. But if you're in two sets, you're also in their intersection. That's again an equivalence. So X is in the intersection of S complement and T complement, right? If you're in the intersection, then you're in both. And so what we've just shown is you are in this left-hand side set if and only if you are in the right-hand side set. That means these two sets have the same elements. And so we conclude that the complement of the union is equal to the intersection of the complements. All right, so that's problem one. All right, let's move on to problem two. Okay, so problem two, we're just given a bunch of little intervals. There's a little empty set at the end, and we have to do some intersecting and unioning, see what happens. Now, before I go into the solution, let me make it perfectly clear why this problem is stumping people. Right? This is not a challenging problem, but it is stumping people because they are misinterpreting this notation. This notation is referring to an interval of points. It is not referring to a collection of integers. So if I try to draw this 4 to 7, people are thinking, oh, look, there's 5 and there's 6, and those are the only things in there. And oh, look, there's a parenthesis, so 7's not even in there. So it's just 4, 5, and 6. And this is simply not true. You are forgetting about all of the real numbers along the way. 4.8 and 5.1 and 2 pi. That's about 6.28, see. there's an infinite number of numbers in here, right? So we have to start with that. Okay, so once you buy that, once you realize this is not just a finite set, then we can solve this problem pretty easily. Okay, so there's 4, 7. Hey, let's draw 2, 6. Well, there's already the 6. And we got to go all the way down to 2. So we'll keep it coming. Okay, maybe there's 3. There's 2, and we don't include the endpoint. Okay, so I would take this little green line, and I get from 2 to 6. Okay, now this yellow line, which we kind of lost here, let me show you where it was. There it is. And what are we doing with these two sets? We are intersecting them. And intersecting means we need things that are in both. So the green and the yellow, where do they intersect? Well, they're intersecting from 4 to 6. Now I had this 4. That's in the set, right? Then we had that here. And that is still inside this set. The yellow from 6 to 7 we lose, and we don't get to include the 6 even because that's not in the set 2 to 6. So at this point, if we just stopped right here, we would have all of the numbers between 4 and 6, including 4, but not including 6. All right. Next, we do a union with 3, 5. Okay, so where's 3, 5? Well, there's 3, and we get to include the endpoint. So let's do this in blue here, right? There's 3, and we get to include all the things up to 5, right? Including 5. All right, but we already had the stuff from 4 to 6. So this blue stuff down here is nothing new. But this stuff from 3 to 4, that certainly is. So when I combine both of these together, I'm getting all the things starting at 3 now and going all the way up to 6. Okay, and then the last thing is I get union with the empty set. And a lot of people on the exam got to here and then just left it blank, right? They just, okay, or just stopped right here. They said, well, nothing more to do. Well, this is like saying some long expression, and then at the end I get 5 plus 0, and then you just refuse to write equals 5, right? I want you to write equals 5, but you just won't do it. And this is the same thing here, right? I'm unioning with the empty set. That means I'm looking at everything that's in both 3, 6, as well as in the empty set. Well, there's nothing in the empty set, so unioning with it is like adding 0. It does not change your set. So this is simply equal to 3, 6, where you include the 3 and you don't include the 6. All right, let's move on to a new standard and problem 3. All right, so problem 3 is part of our second standard, basics of functions. And we're given 3 sets, S, T, and U, and functions f from S to t, g from t to u, and we're told that these are surjective functions. So if we draw a quick picture here, we have s going to t via f, followed up by g going from t to u, and each of these is a surjective map. The first question is what is the domain of the composition? Okay, so composition is what happens when I do this entire map now, going from S to U, right? Which is given by first applying F and then applying G. So the domain of this function is S, and the codomain of this function is U. All right, now we have a proof. Prove that the range of G composed F equals the codomain of G composed F. Okay, so the codomain of G composed F is U, and we want to show that this is equal to the range. So the range is all of the elements that are actually images of the map, okay, the actual images. So to show that the range equals the codomain, right, well, we always know that the range is a subset of the codomain. That's always the case. So we need to show that everything in the codomain is in the range. So we'll start by taking something from the codomain and showing that it is in the range of G composed F. Well, if I have something in U, then I know U is an image of G. So since G is surjective, there exists some T in T such that G of T is equal to little u. Okay, so I'm able to pull back and I get an element of this intermediate set T. But I also know that F is surjective, and so T is an image of F. So since F is surjective, there exists some S in S such that F of little s is equal to little t. Okay, so I started with a little u and u, and I was able to pull back to an element S and S. Therefore, if I apply the composition G composed F to S, this will be the same as G of F of S, which is G of T, which is equal to U. And therefore, S is a preimage of U. Okay, so I've just shown for every element in U, there is a preimage, meaning that U is in the range. All right, thus U is in the range of G composed F. All right, so everything in the codomain is in the range. We conclude the range equals the codomain. Okay, so there's the proof. Now, of course, what this is really doing, right, is showing, right, this shows G composed F is surjective, right? The range of a function equals the codomain if and only if that function is surjective. So in this case, the function is the composition. Okay. Now, it is not enough for you just to say, well, yeah, these are surjective, so their composition is surjective, and so the range is equal to the codomain. This question is asking you to prove that fact, right? That the composition of surjective functions is surjective, right? Or at least something equivalent to that. But you can't just cite that and say, oh, look, I proved it. All right, let's move on to problem number 4. All right, in problem number 4, it's a true or false question, although it does not say we don't have to explain, so we better explain it. Let's see, for sets S and T, a function f from S to T is injective if and only if for every S and S there exists a unique T and T such that f of S is equal to T. Well, this sounds like it could be right. It's saying you have one input and that goes to one output, and that kind of sounds like one-to-one, except one-to-one doesn't mean what it sounds like. Okay, injective functions, right? Injective functions are ones for which every element in the codomain have at most one preimage. So if I have my function f going from S to T, f is injective if and only if for every element in T I have at most one preimage, meaning I have at most one arrow going in, right? So I could have this, that, I could skip one, that's fine, that's fine, I'll skip another one. Okay, this would be fine. What would not be fine is if I had 2 arrows going in to one dot. All right, that would not be good. Okay, so we'll get rid of a red line there. All right, so injective, right? Injective means for all T and T. Okay, so this is very important. You're not starting with an S and S, you're starting with a T and T. For all T and T, there exists at most one S and S such that, right, and this is F injective, such that F of S equals T. Okay, now, what does this actually represent? Well, if for every S and S there exists a unique T and T such that F of S equals T, that would actually be this picture where you're saying, oh, okay, so I have my S, I have my T, I put in my dots, and for every S and S, okay, there is a unique T. So there's only one arrow coming out of each of these dots, and it does go into T somewhere. Now, maybe some of them go to the same place, that's fine, all right? But it's saying there's only one arrow coming out, and it has to go into T. This is actually the definition of a function, right? So this whole thing is the definition of a function. So this is not talking about an injective function, it's just talking about any function. So this is a false statement. Okay. All right, let's move on to problem number 5. All right, in problem 5, we're asked to give an example of a function with domain the real numbers and range the integers. Now, we have to be very careful here because, okay, the domain being the real number says, okay, it has to be defined, any real number you want. But I'm not expecting too many people to mistake that. But over here, this is saying the range. This is not saying the codomain, right? So for example, well, I'll do it in red since this is a non-example, really. So here's a non-example. What if I take f r to z, which is just the constant function, f of x equals 0. So certainly the codomain is the integers. However, the range is just the single point 0. Here's another non-example. What if we do the characteristic function or indicator function on the rationals? So this is the one which is going to take some x and it sends it to 1 if x is a rational number and 0 if x is an irrational number. Again, this has the property, it's defined on all real numbers, the output is definitely an integer, but the range is not the integers. In fact, it's just the two numbers 0 and 1. So we need a function that is actually going to hit all of the integers at some point. So a good example of this would be the floor function. So the floor function, so this just takes some real number and it returns the largest integer greater than, or rather, greater, less than, it's the floor, less than or equal to x. So for example, if I had the floor of 3.4, this would return 3. Okay? 3 is the largest integer, which is less than or equal to 3.4. If I had just 2, well, this just, of course, returns 2. If I have negative 0.8, right, the largest integer, which is less than or equal to this, is going to be negative 1. All right, so this is going to give me all the integers, right? In fact, if I take an integer, so if n is an integer, then the floor function of n is just equal to n, right? N is the largest integer, which is less than or equal to itself. In fact, it's equal to itself. All right, so that is a reasonable answer to this question. Of course, you could also use the ceiling function, right? So the ceiling function looks like the floor function, only you put the roofs of the brackets on top, right? The ceiling of x, right? This is equal to the smallest integer greater than or equal to x. Okay, so this will work in almost the exact same way and be fine. Now there's kind of another, nice hack way to do this, right? So here'd be another nice example. So let's say I have some g, goes from the reals to the integers, and using this floor ceiling idea where, look, when you apply it to the integers themselves, you just get back the same integer. Well, what if I just do that? What if I say g of n equals n for all n and z? So as soon as I do that, I know that my range is at least going to be the integers. And then where do I send everything else? Well, it doesn't matter. I can just send it anywhere I like. So I could send g of x equal to, I'll just pick something easy, right? 0 for all x in the real numbers, not in the integers. Okay, so it sends the integers to themselves and it sends everything else to 0. And that would do it. All right, so of course, lots of ways that you could do this. Okay, so let's move on to problem 6 and a new standard. Okay, so problem 6, our next standard here is going to be about absolute values and inequalities, and in this problem we want to prove something we've used quite often this semester, namely that if a and b are within epsilon of each other, where epsilon is some positive number, then b is in the a coin of radius epsilon, right? That is, b is between a minus epsilon and a plus epsilon. So there's a lot of ways for us to start this. Why don't we use sort of the last definition of absolute value we wrote down, which is that the absolute value of a minus b, which of course we can think of as the distance between a and b, but we also can write it as the maximum of a minus b and the negation of a minus b. And what this tells us is that each one of these two is less than or equal to the absolute value of a minus b. So that means that a minus b is less than or equal to the absolute value of a minus b, which is less than epsilon. That's by assumption. And so if I add b to both sides and subtract epsilon from both sides, I'm going to end up with a minus epsilon is less than b. And that's kind of the first half of this here, right? This here, right, we could think about this as saying b is between a minus epsilon and a plus epsilon, and we've just proved the left-hand side. Okay, but on the other hand, we know that the negative of a minus b is less than or equal to a minus b absolute value, which is less than epsilon. But the negative of a minus b is equal to b minus a. And so now if I add a to both sides, I end up with b is less than a plus epsilon. And that's the second half of this inequality. And that's it. Between the two of these things, we conclude that b is greater than a minus epsilon, but less than a plus epsilon. Okay, and there it is. All right, let's move on to problem number 7. Okay, so in problem number 7, we're asked to identify which one, so there's only going to be one of them, of the following statements is always true. All right, well, let's see. So the first statement, this looks somewhat familiar. You're looking at the difference between the absolute values of a and b is greater than or equal to the distance between a and b themselves. Okay, now this looks suspicious. I kind of remember something like this, but with the inequality going the other way. So that makes me think this one might not be true. Can we construct an example? Well, here's the key. I know the right-hand side is an absolute value, so this is definitely going to be greater than or equal to 0. On the other hand, it's very easy to construct examples where the difference of two non-negative numbers is negative. So for example, if a was equal to 3 and b was equal to 8, then the absolute value of a minus the absolute value of b would just be 3 minus 8, which is negative 5. And, well, if I do the absolute value of 3 minus 8, that's going to be equal to 5. So yeah, you can see here, this is not, there's just no way this one is going to work. Okay, the next one. If A and B are more than D apart, then A is in the B coin of radius D. Ooh, well, this looks a lot like the previous problem, number 6, except something is backward, right? This one is saying the distance between A and B is greater than D, whereas before the distance between A and B was less than epsilon. So yeah, I don't think this one's going to work out. But let's make an example. So let's say that, well, we'd use actually the same A and B. So if A is 3 and B is 8, then the distance between 3 and 8, well, we just saw that, it was equal to 5. And, well, what is 5 greater than? I don't know. How about we'll make it 2? Okay, so this is greater than 2. Is 3 in the coin, the 8 coin of radius 2? So 8 minus 2, 8 plus 2, which is 6 comma 10. And of course, no, definitely not. 3 is not in there. Okay, so B is not true. Okay, C. If A is less than B, then A times D is greater than B times D. Well, this again feels backward, but we do remember there's that situation, right? Inequalities will reverse if you multiply by negatives. But, well, what if we don't? What if I take the exact same A and B, so 3 is definitely less than 8, and I multiply by, I don't know, how about D equals 2? Then I would have 3 times 2 is still less than 8 times 2. Right? This is 6 and this is 16. So the inequality didn't get reversed, so it's not C. Okay, part D. If A is less than B, then A plus D is greater than B plus D for D negative. Well, let's see. If I take 3 less than 8, that is still a good example for A and B, and I add a negative number, does it change the inequality? Well, let's add, how about we'll make D equal to, I don't know, negative 2. Then I would have 3 plus negative 2 and 8 plus negative 2. But 3 plus negative 2 is 1, and 8 plus negative 2 is 6, and well, 1 is still less than 6. It did not change the order of the inequality, so it's not D. All right, let's check E. E says Dr. Glesser, hey, that's me, messed up again, and all of the above statements are false. Yep, look at that. Look at that. All of them are false. We had to come up with examples for each. Okay, we're going to move on to problem 8 and a new standard. Okay, we move on to our fourth standard. This one is all on the supremum, the infimum, axiom of completeness, and while we won't have a problem on it here, this standard does include the nested interval property. All right, so problem 8, we're given two bounded non-empty subsets of the real numbers. Yeah, I think in the exam I didn't write the word bounded, but of course this problem doesn't mean a whole lot if they're not bounded sets. Let's see, and then A and B, well, we're going to add them together. And when we add them together, we get all possible sums, right? Something from A, something from B. And we want to prove that the infimum of this sum set is at least as big as the sum of the infima of the original two sets. And actually, this isn't just greater than or equal to. It turns out this is equality. Maybe I'll prove that. But let's get to the proof of what was on the exam first. So let's see. We know that the infimum of A is at least as big as everything in the set A. So if little a is in A, then A is at least as big as the infimum of A. Okay, and this because the infimum of the set A is the greatest lower bound. All right, so the greatest isn't important here for this step. Right? We know the infimum is a lower bound for the set A, so it is less than or equal to everything in the set A. And similarly, if B is an element of B, then that element B is at least as big as any lower bound. In particular, it's at least as big as the infimum. But now we have a property of inequalities that says if I start adding numbers to both sides, right, of an inequality, it's not going to change things. Okay, so I can add A and B together, and that is going to be at least as big as the infimum of A plus the infimum of B. All right, I can replace B by something smaller, A by something smaller. The inequality still holds. Okay, so the combination of these two implies that. All right, now A plus B is some generic element of the set big A plus big B. And we've just shown now that every element of A plus B, right? So this implies every element of the set A plus B is at least inf of A plus inf of B. Okay, so this tells us that the sum of the infimum of A and B is a lower bound for the set A plus B. So the infimum of A plus the infimum of B is a lower bound for A plus B. Okay, but we know that the infimum of a set is the greatest of all lower bounds, and so the infimum of A plus the infimum of B must be less than or equal to the greatest lower bound of A plus B. So the infimum of A plus the infimum of B is less than or equal to the greatest lower bound for A plus B, which is the infimum. And well, other than it's written in the opposite order here, like these are the same thing. Okay, so we've proved what we needed to prove on the exam. Okay, let's just, you know what, why don't we just prove the reverse inequality here, just so you've seen a proof of it. It's a really handy thing. So, right, so let's now prove that the infimum of a plus b is less than or equal to the sum of the infima. And this is actually a little bit tricky to do until you've, well, seen the trick, right? It's not like super obvious what you're supposed to do, but again, it will come down just to the definition of the infimum. So let's see what we have here. We know that if I have an element from A and an element from B, okay, so if A is in A and B is in B, then I can add them together and get an element of the set A plus B. So then A plus B is an element of A plus B. Okay, now the infimum of A plus B is a lower bound. So that tells us that the infimum of A plus B is less than or equal to A plus B. And this is true for all A, and it's true for all B and B. So here's what I want to do. I want to fix a particular A in A. Okay, so let's just fix A in A. Okay, so it's just that's going to stay the same. Okay, so I subtract A from both sides. So now I have that the infimum of A plus B minus A is less than or equal to B. And this is a true statement for all B and B. Okay, so A is fixed. That's just some element of A. I have the infimum, that's fixed. But this number here is a lower bound for the set B because it is less than or equal to little b for all B and B. So this implies that the difference between the infimum of A plus B and this fixed element A is a lower bound for the set B. Okay, but we know that the infimum of B is the greatest of all lower bounds. And so this implies that the infimum of A plus B minus little a is less than or equal to the infimum of B, because the infimum of B, again, is the greatest of all lower bounds. Okay, and this was true for any A we picked, right? We fixed one of them, but this is always going to be true. So let me now move this A back over to the right, and I'll move the infimum of B over to the left. So I get that the infimum of A plus B minus the infimum of B is less than or equal to A. But again, this is true for all A and A. Okay, so now I'm unfixing my A, right? Unfix A. Okay, which means that this difference between the infimum of A plus B and the infimum of B is a lower bound for the set A. But again, the infimum of A is the greatest of all lower bounds. And so that tells me that the infimum of A plus B minus the infimum of B is less than or equal to the infimum of the set A. And now adding the infimum back to the right, we get that the infimum of the sum is less than or equal to the sum of the infima. Okay, and that's what we wanted to prove in the second part. Okay, and so the combination of these two parts allows us to conclude that the infimum of the sum of A and B is actually equal to the sum of the infima. And again, of course, this assumes that both A and B are, well, at least lower bounded so that infima exist. Okay, whew. It wasn't that long on the test because, well, we only had to do 1/2 of it. All right, well, let's move on to problem number 9. All right, in problem number 9, we're asked to use the axiom of completeness to prove that the set of positive integers is unbounded. All right, so this is a classic proof, and I think I might make a video that actually talks about why this is even something you'd want to do. Because normally you're thinking, hey, it's the positive integers. It just goes on forever. That's obviously unbounded. And yet it actually does have something to do with the way we embed those positive integers into the real numbers that actually makes it unbounded, because we can actually give an example where the positive integers are contained in an ordered field and yet they're bounded. Okay, so I think that may be a video down the line we'll do. But let's actually give a proof that shows why the axiom of completeness is useful here. So we're going to, of course, assume that it's not bounded, or that it is bounded rather. So assume that the set of positive integers is bounded. Okay, and we do that so that we can use the axiom of completeness, because the axiom of completeness tells us that every non-empty bounded subset of the reals has a supremum. So, of course, the positive integers are non-empty. So assume that they're bounded. So by the axiom of completeness, the supremum exists. Okay, fine. So I have this real number, the supremum of the positive integers. Doesn't have to be an integer itself, but it's just some real number. It exists. Okay, fine. Let me subtract 1 from it. Okay. So if I subtract 1 from this supremum, this can no longer be an upper bound for the positive integers. Why? Because if it was, then I would have broken that the supremum is the least upper bound. Okay, so this is not an upper bound for the positive integers. Okay, fine. Well, if it's not an upper bound, that means there must be some positive integer which is greater than it. Okay, so thus there exists some positive integer x such that the supremum minus 1 is strictly less than x. Okay, but if that's true, and I add 1 to both sides of this inequality, then I get that the supremum, now without the minus 1, just the actual supremum, is less than x plus 1. And x plus 1, well, x is an integer, and 1 is an integer, positive even, and so this is a positive integer. And this is a contradiction, okay? So a contradiction since the supremum is an upper bound for the positive integers, and yet I just found a positive integer which is greater than it. Okay, and so that's the whole proof. Yeah, not actually all that difficult, it turns out. Again, though, we are very, very much using the axiom of completeness here to make this argument. And yeah, I hope to get to make that video in the future showing why this this claim that Z is unbounded can actually fail in certain ordered fields. All right, let's move on to problem 10. Okay, so in problem 10, we're given a function defined on the interval 0 to 5. And let's see. Okay, so from 0 to 3, it is linear. And it's probably helpful to us, right, if we maybe try to give a little graph of this. So from 0 to 3, so let's see, 1, 2, 3, I guess we're going to go all the way to 5s. So we'll mark our graph a little bit here. Just the way we learned. Okay, so 2x plus 4 is just a line. When x is equal to 0, we are at 4. So let's see, maybe we'll put 4 about there. Okay, so there's at 0. Let's see, well, we can just plot a couple points. When x is equal to 1, we'd be up at 6. When x is 2, we'll be up at 8. Oh, and maybe we'll want to go just a little bit higher with our graph, because now we'll be up at 10 when we get to 3. Okay, and then we can connect these dots, la 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 la. Okay, now we get to 3, and it's going to hop to x minus 5 cubed. Now, this is a cube, but it's been shifted over by 5. So what's going to happen when x is 3? Oh my goodness, it's going to be very low, right? 3 minus 5 is -2. -2 cubed is -8. Oh, that's way down here, right? So there's -8. But of course, we don't actually get this thing. And then it's going to go up to 4. 4 minus 5 is -1. -1 cubed is -1. Okay, so that's going to be here. And now let's see. If x had been 5, now I know we're not allowed to use 5, but then we'd be at 0. And in fact, if we just on the side remember what x cubed looks like normally, okay, it's looking like this. This x minus 5, of course, has translated the axes to the left by 5. And so if we translated it, then it would look something like this. Okay, so what we must be getting, since we're to the left of 5, we must be getting all this stuff going up. So it's definitely just increasing from between when x is between 3 and 4. Okay, and that's important because if we're trying to figure out, for example, I don't know, say suprema and infima, it's good to know if your graph is increasing or if it may be going up or going down, because we need to check possibly in between the endpoints what's going on. Okay, and then finally from 4 to 5, we have the absolute value of x, so that's really easy. Between 4 and 5, like the absolute value doesn't even like appear, like you just get x itself. So we're going to get 4, and then of course 5 is going to be down the middle here, and it doesn't actually hit at 5, but it gets pretty close. Okay, and it's again increasing. So all these things are increasing, so it turns out checking the endpoint is enough. Okay, now we're asked to compute the suprema and the infima of the range of f. And so we can see very easily from this graph that the suprema is going to be 10, right? That's the highest point of the graph, and it actually is in the set, although even if it wasn't, that wouldn't be a problem. So this supremum is equal to 10, and the infimum, well, let's see. The lowest point is occurring down here, and you might say, well, it doesn't actually hit this -8, but that's okay because it's just supposed to be the greatest lower bound. It doesn't actually have to be in the set. So our infimum is going to equal -8. Okay, and it's important in here, right? These were all increasing functions. Let's say we'd had some sort of parabola in our set, right? And we were saying, oh, I'm trying to find say the supremum, and I looked at a set, maybe it started here and it ended here, and I say, oh, well, if I only check the endpoints, I'm going to think maybe this is the highest point at 0, and this is the lowest point over here. But of course, there's this guy in the middle who's much, much higher. Okay, so we have to make some sort of an argument, whether by graph or with words, about what is the actual shape of the graphs we're looking at. Otherwise, we can't make these kind of claims. Okay, let's check out problem number 11. So problem number 11, hey, we've actually did this when we were back in problem number 9. We just need to state the axiom of completeness. So every non-empty upper bounded subset of the real numbers has a supremum. And of course, if you have a lower bounded subset, non-empty, it will have an infimum, which we can prove actually is a consequence of this version of the axiom of completeness. Okay, let's move on to a new standard and problem number 12. Okay, on to our next standard. This is all about cardinality of sets and distinguishing countable and uncountable sets. And in problem 12, we want to describe a bijection from the positive integers to the rational numbers. So it's not going to be like super easy to write down an explicit rule, right? We can write down a function that, well, we can tell you what it's going to do, right? but writing down an explicit formula might be a little trickier. So for now, we're just going to stick with a description of one. So here's what we're going to do. Since we're trying to get a bijection, that means it needs to be surjective. And that means we're going to have to hit every single rational number. Of course, we don't want to hit anything twice, so we got to be a little careful about that. So the way we're going to do this is, and this is the way we did it in the lecture, is we're going to say, well, every rational number is going to be of the form a over b, where a and b are integers and b is not 0. Now, of course, what I could do, right, once I get some a over b, is I could make an assumption that, well, okay, if there are two negatives, I just cancel the negatives. If there's one negative, I could always put it on top or bottom, but let me just say I'm always going to put it on top, so I can even assume my b is positive. And then I could reduce, right? I could reduce my fraction, and if I do that, then I'm basically saying that the GCD of a and b is 1. Okay, so if I had 3 over 6, I would reduce this to 1 over 2. Okay, fine. So if I take any rational number, I can always reduce it and make sure that the denominator is positive. Then what am I going to do? Well, I can look at the two numbers I get when I reduce it, and I can ask, what do they add up to? And the smallest I could possibly add up to would be 1. And that would occur, well, I can't let b be 0, but I could let a be 1. Of course, I could get negative 1, but let's just talk about positive for a second. Right? So I'm going to build a set, and we'll call it a sub 1, and it's going to have 0 over 1 in it. Now, of course, again, well, for numerators, I can't use a 1 here, because then it would add up to 2. This is the only thing I get. I can't put a negative on the bottom because of this condition. So there you go. That's everything where the numerator plus denominator add to 1. And what I'm going to do is I'm going to define a function, f, from the positive integers to q. And I'm not going to be able to write down an explicit formula for f, but I'm going to start telling you what it does. And so the first thing I'm going to tell you is that f of 1, okay, that's going to be the first positive integer, is going to map to, well, this one unique element of a1, which is 0. Okay, let's move on then a2. So a2 is going to be all of the fractions where the numerator and the denominator add up to 2. And I can do that in, well, actually only one way, 1 over 1. And I'm actually going to modify what I said just slightly. I'm also going to put in the negatives. Okay, so I'm going to take this, and then I'm going to union it with the negative versions. Okay, so this will be negative 1 over 1. So these here are all the ones where the numerator plus the denominator in absolute value add to 2. Okay, I didn't have to worry about the absolute value in the first one. Okay, and so then I'm going to say, okay, fine, f of 2 is going to be 1 over 1, which is 1, and f of 3 is going to be negative 1. Fine, what about a3 now? Well, I keep going. So now I want to look at all the things where they add, the numerator and the denominator add up to 3. So let's see. And I was doing these as sets before because, well, there was only one thing to write down. But you know what? What if we write these as lists? All right. So I'm going to write these as lists. So I'm going to use the parenthesis notation, which tells me that order is going to matter. And that way I have some sort of a consistent way that I write these down. So, well, let's see. If they're going to add up to 3, I could do 1 over 2 and 2 over 1. Or 0 over 3, but if I did like 0 over 3, right, like the GCD wouldn't be 1. So I get 1 over 2 and 2 over 1. Let me do it always so that the numerator is increasing. So I'll have 1 over 2 and then 2 over 1. And then I'm going to union it with another list, okay, which by union here, I just actually mean concatenate. And I'm just going to do the negatives of them. Okay, so -1/2 and -2/1. And so now I'll just continue defining my function term by term. F of 4 will be 1/2. F of 5 is going to be 2. F of 6 will be -1/2. And F of 7 will be -2. Okay, let's do another one. So now I'm going to be adding up to 4. So I could do 1, 3. I would do 2/2, but that actually would violate the GCD of A and B being 1 condition. So I don't need to do 2/2. And then I can do 3/1. Okay, and then I'll do the negatives. So -1/3 and -3/1. And so now I can continue. F of 8 is 1/3. F of 9 is 3/1. F of 10 is -1/3. Okay, of course, 3/1 is just 3. And F of 11 is -3. Okay, I'll do one more. I'll do one more here. So for A5, so now they have to add up to 5, so I can do 1/4, 2/3, 3/2, and 4/1. And then I have all the negatives. So -1/4, -2/3, -3/2, and -4/1. Okay, and so, well, I'm not going to write all these down. F of 12 would be 1/4. F of 13 would be 2/3. And we continue on in this way. Okay, and so in general, AN is going to equal the union of two lists, right? So this is just going to be the negative of the left list. And this list will consist of all reduced fractions whose numerator and denominator sum to n ordered by increasing numerator. All right, and so there we go. And we can then apply F just in order to these, right? So apply F in order. And the idea here is, if I have any fraction Q, I know it has some reduced form, and then I can add the numerator and denominator, so I know it will show up in one of these sets. Therefore, this function will be surjective. On the other hand, F is going to be injective because, well, a fraction only has one reduced form. So it's only going to show up in one of these sets. Okay, so that's how we build the bijection F. Okay, let's move on to problem number 13. Okay, so in problem number 13, we're asked to classify 6 different sets as being finite, countably infinite, or uncountably infinite. So let's see. The first one is the Cartesian product of 2 copies of the rational numbers. And we know each one of these is, I'll just abbreviate here as CI, is countably infinite. So we had a countability omnibus lemma that told us that if you take a finite Cartesian product, okay, so here there's just 2 of them, that's finite. If you took a finite Cartesian product of countably infinite sets, you would still get a countably infinite set. So this set will be countably infinite. Now, if you said an infinite Cartesian product of countably infinite sets, then you'll get an uncountably infinite set. But with just 2 of them, you're okay. Let's see, the next one. This is an interval, okay? Mind you, this has lots of numbers in it. This has all the real numbers between 2 and 4, not containing the 4, of course, but are containing the 2. This is a real interval, okay? And we actually proved as part of our uncountability omnibus lemma that any real interval is uncountably infinite. All right, the next one, the set of real numbers between 1 and 2 that start with an 8 after the decimal. All right, so we're looking at things that are going to look like 1.8 and then stuff, right? So maybe, I don't know, 4057, dot, dot, dot. Okay, well, first, what if I took this number and multiplied it by 10? Okay, so if I multiply this by 10, I'm going to get 18.4057. Okay, and then what if I subtracted 18 from this number? If I subtracted 18 from this number, I'd end up with 0.4057. Okay, and now here's the idea. When I multiply by 10, that is actually a bijection, right? I take 10, the function f of x equals 10x is a bijection. And if I subtract 18, right, if I take the function g of x equals x minus 18, this is a bijection. So there's a bijection between the set of real numbers between 1 and 2 that start with an 8 after the decimal, like this, and numbers that are just between 0 and 1, right? If I multiply by 10, that gets that 8 out of the decimal, and subtracting 18 is going to get rid, right, of all this stuff in front of the decimal. So I'm left with just some number, right, which is in between 0 and 1. And we know that this set is, again, it's a real interval. It is uncountably infinite. All right, next we have the set of roots of sine of x. So yeah, a lot of people said this was finite. I imagine it's because you're thinking of, well, okay, yeah, sine of 0 is 0, and maybe sine of pi is 0 or something, and you stop there. But of course, you know that the sine function, right, it goes on and on and on in both directions, right? And it's going to keep on hitting the axis all the time, where 0, pi, 2 pi, negative pi, and so forth. In fact, the next time, right, it's going to hit it is going to be at 3 pi, and then at 4 pi, and so forth. And in fact, we can count all of those intersections, right? It's just some positive integer times, or some integer rather, times pi. And of course, the integers are countable. So this is a countably infinite set. All right, part E, the set of all subsets of a countably infinite set. So this is also known as the power set, right? Well, if I drop the last bit, okay, the set of all subsets is called the power set, okay, of whatever set you're talking about, right? So this is the power set of a countably infinite set. And we had our uncountable or uncountability omnibus lemma tells us that the power set of an uncountably, or rather of a countably infinite set, is uncountably infinite. Okay, and then finally we have the intersection of these intervals. Well, this is just a 4-coin of radius 1 over n. And we've seen this type of interval a lot this semester. I have 4, 4 plus 1 over n, 4 minus 1 over n. As I let n get very big, this 4-coin is going to get very small. And in fact, since I'm taking the intersection, I want to know what are the only points that are in all possible 4-coins. And the answer is there's only one point, and that's the point 4. And so this is a finite set. Okay, so that's everything we got for cardinality. We'll come back next with 14, our next problem. Okay, we move on to our next standard, which is applying Cantor's diagonalization argument to prove a set is uncountable. So in problem 14, we're given a set A, which is the set of all sequences, A dot, where for all n at least 1, we have that an is in 0, 1. So these are sequences of numbers that only contain zeros and ones. Okay, fair enough. And we want to show that this set A of all such sequences is uncountable. Okay, and we're going to use Cantor's diagonalization argument. So here we go. Well, Cantor's diagonalization argument is always going to start by assuming that your set is countable. So assume, well, what does it mean if A is countable? Assume A is countable. Well, it means that there's a bijection i.e. there exists a bijection, let's call it F, from the positive integers to A. All right. Fine. What I want to do is, knowing that F is a bijection, that means it is surjective, I'm going to build an element of A that is not in the image of F. Okay, that's the key idea here, right? So the key idea is to construct an element of the set A that has no F preimage. Of course, this will be a contradiction because F is a bijection, so it's surjective. Every element of A has a preimage. Okay, so how are we going to do it? So we're going to define a sequence. Let's see. Since that's already an A is a generic one, I don't know, we'll call it like X dot or something. Okay, so we're going to define a sequence X dot. And what is the sequence going to look like? Well, how about we'll call the first term, not E, but x1, and the next term x2, and then x3, etc. All right, fine. How are we going to define it? All right, by So I want to define x, k, in two different ways, okay? It's going to depend on what the value is when I look at certain terms, right, of A. So what I'm going to do is I'm going to look at f of, say, k. So k is some positive integer. And what is f of k? Well, it has to be an element of A. And that means it's a sequence. So it's going to look like A1, A2. Well, it actually depends on the k, so why don't we put that into the notation? It's going to be AK1, AK2, AK3, etc. Okay, so I take f of k, it gives me some sequence. And the way I'm going to define xk is by looking at the kth term in the sequence corresponding to k. Okay, that is, I'm going to look at AKK. So I'm going to say, okay, what does AKK equal? Okay, well, let's see, we'll make that a little lower. I know that everything is going to be either a 0 or a 1. So if AKK is equal to a 0, then I'm going to define x sub k to be 1. And if A sub kk is equal to 1, then I'm going to let xk equal 0. So it's going to be whatever akk is, xk is going to be the opposite. Okay, but because f is a bijection, it is a surjection. So since f is surjective, f, or rather x dot, has a preimage, right? In fact, we say an f preimage. Okay, as long as x dot is an A, which it is, okay? The way we defined it, it is a sequence that only has zeros and ones, right? So x dot is an element of A. So x has an f preimage, right? i.e., there exists some, I don't know, say m positive integers such that f of m is equal to x. Okay, but here's what we know. X is equal to x1, x2, etc. And x dot is equal to f of m. And f of m is equal to, well, the sequence a m1, a m2, a m3, etc. So I have two sequences, one on the left, one on the right, and they're equal, which means they're equal in every single component. But if they're equal in every single component, then for sure they're equal in the mth component. So this implies that the mth component, which is x sub m, is equal to the mth component on the right, which is a m m. But this is a contradiction because of the way we defined our x sub k, right? Any of our x's, it was always different in the kk position, or if we're looking at xm, the mm position. So this is a contradiction. Okay, where did the contradiction come from? It came from our assumption that A is countable. Therefore, A must be uncountable. Well, at least as long as it's not finite. Okay, let's move on then to problem number 15. All right, so in problem 15, this is actually a repeat of a problem from Superquiz 1. It says in Cantor's diagonalization argument, one assumes, for the sake of a contradiction, that the set 0, 1 can be written out as a list. One then produces an element of 0, 1 that is not on that list by building a number that differs from the nth number on the list in the nth position. This should sound a lot like what we did in the previous problem. Explain why this argument fails to show that the interval 0, 1 intersected with Q is uncountable. Okay, let's backtrack a moment. Let's go back actually to problem 14. We made this very crucial assertion. When we defined a sequence, this x dot, we had to add this extra little note here, right, that x dot was actually in A. Okay, and once we did that, then we could say, oh, cool, so we know that if it's in A, then since f is surjective, then x dot has an f preimage. Now, let's go back to this problem. When we try to apply Cantor's diagonalization argument in this situation, we would build a number between 0 and 1, but if we build that number, and maybe we called it E1, 0.E1, E2, E3, etc., this argument only works if we know that this, not x dot, just x, if we know that this number x is in the image of the bijection, right? So here we would need to have a bijection from the positive integers to Q. And if we knew that x was in Q, then it would have an f preimage, and then we could continue on with the argument. And this is the issue. When we build the x in the way that we try to build it using Cantor's diagonalization argument, there is no guarantee, in fact, no reason to even think, that this x is in Q. Okay, so likely x is not an element of Q. And if it's not an element of Q, this means x has no f preimage. Okay, and you go back up here. Once you knew you had a preimage, then you could do this equality, and that's where the contradiction came from. Without having that preimage, you can't build the equality, you can't get the contradiction. Okay, well, that's number 15. We'll move on next time to a new standard. Okay, the next standard is all about limits of sequences. And this problem, this is a classic, right? We're going to prove that the limit of a sum is the sum of the limits. Now, it is important that you don't just use the theorem, the algebraic limit theorem, saying that the limit of a sum is the sum of the limits. We really want to prove it here. All right, now importantly, we notice we are given the key assumptions that the limits of the two sequences, A and B, actually exist, and we know what they're equal to. Okay, if we did not have that, we could not conclude the next line. Okay, fine. What are we going to do? Well, we need to go back to the definition. What does it mean for sequences to converge? So if I want to show that the limit of a sum of two sequences is equal to k plus L, then I need to show that I can find a tail, right? Which is going to be contained in, well, okay, you got to give me some k plus L coin, right? So you say, oh, here's a k plus L coin. I want to contain a tail of the sequence, so I got to find that tail. So we're going to start by saying let epsilon be greater than 0. All right, that's going to be the radius for my k plus L tail. Fine. Well, I have already two limits, right, that I know exist, right? A converges to K, B converges to L, which means for this given epsilon, I could find a tail of A, which is contained in the K coin of radius epsilon, and I could find a tail for B, which is contained in the L coin of radius epsilon. Now, they're probably not going to be tails that start at the same place, but of course I could always go out to the max. And we make that really short by just using the Mick theorem. So by the Mick theorem, right, this is our multiple constraint theorem. By the Mick theorem, there exists some, let's call it P of epsilon, such that if little p is at least big P of epsilon, then A sub P and K, as well as B sub P and L, are within epsilon of each other. Okay, so I can just do this all at once using the Mick theorem. Okay, now we aren't interested so much in AP minus K or BP minus L, but rather in what happens when we look at maybe say AP plus BP minus the sum of K and L. So let's do it. We have that if we do AP plus BP, now this is the pth term of the sequence A dot plus B dot. And I want to know how far away that is from K plus L. In fact, I'd like to get it less than epsilon. Well, we can rearrange things. And if I do, I'll get AP minus K plus BP minus L. And now I can use the triangle inequality to break this absolute value up as the absolute value of AP minus K plus the absolute value of BP minus L. And from what we saw in the previous line, we know that these are bounded by epsilon. So this is bounded by epsilon plus epsilon, which is 2 epsilon. Hey, you know what? That's not quite epsilon, but it's good enough. By the inspired choice theorem, A dot plus B dot converges to K plus L. There we go, we're done. Okay. Yes, of course, we could have gone back and made it so that, oh yeah, if we go out far enough, these are all less than epsilon over 2, but why bother, right? This 2 is some positive constant, inspired choice theorem. We're all done. All right, let's check out problem 17. Okay, so in problem 17, we are given an explicit sequence and just asked to find the limit of it. This is a problem we could have done way back in Calc 1 or Calc 2. Let's see, so what's the idea? Well, let me tell you what the idea isn't, right? You might be tempted to say, well, this is a sequence defined with a quotient, so if I want the limit of the quotient, I should take the quotient of the limits. That's not going to work here, because check out this numerator. This is a sine function, and as n goes to infinity, I mean, who knows? This is just going off to infinity. The sign's going up and down. Like, there's nothing good happening here. So the limit of the numerator just doesn't exist, and so we can't use the algebraic limit theorem here, right? We just cannot break this up as the quotient of the limits. So we are going to have to be a little more clever here, right? But we do know some things about the sine function. For example, we know that the sine function is always at least -1. We also know that the sine function is always no bigger than +1. Now, this denominator here, since everything's got a plus sign, I know that this is at least 0, right? We're actually greater than 0. So I could divide by this, never going to have any sort of a problem. So what if I just divide each of these? Not only is it defined to divide by it, but because this is positive, it's not going to change the direction of the inequalities. So I just do this everywhere. And now I notice that my sequence, right, the nth term is actually lying right in the middle. And it's a lot easier to actually figure out what's happening to these guys on the left. I have a constant on the top, And on the bottom, I have a sequence going to infinity. So we know that these outer bits go to 0, right? But if I know that the outer limits go to 0, then by well, that's right, the squeeze theorem, I know that the inner bit goes to 0. And so we conclude from this that the sequence C converges to 0. Okay, let's move on to problem 18. Okay, so here in problem 18, we get a visit from our good friend, Clever Carl, who's trying to prove that the limit of a sequence A is equal to L. So he chooses an epsilon greater than 0. Hey, that's a good start, Carl. And he finds an n of epsilon, a positive integer, such that if n is at least n of epsilon, then the difference between the nth term and of the sequence A and L is less than negative 3 times epsilon. Okay, that's kind of weird, but what happens? He concludes by the inspired choice theorem, we have the limit of A dot is equal to L. Is this okay? Well, here's the problem. Okay, let's write down the inspired choice theorem. Okay, so the inspired choice theorem, or we'll just abbreviate it here as the Inch theorem, it says that A dot converges to L, right, or the limit of A dot equals L, if and only if for all, let's start over. If and only if there exists a positive constant K, such that for all epsilon greater than 0, there exists an n that depends on epsilon, positive integer, such that if little n is at least n of epsilon, then the difference between an and L is bounded by k times epsilon. Okay? And we just cannot overstate how important that this k is a positive constant, right? How important that is. Because if k was 0, for example, then you'd be trying to get this difference to be strictly less than 0. Well, but this is going to be a non-negative number. That's just impossible. And it's even worse when you put a negative number in for k, right? So if we have negative 3 here times epsilon, that means that since epsilon is positive, this expression is negative. Now, a lot of people wrote down, oh, this gives us a negative epsilon. Well, I think I know what you're trying to say, but epsilon is still positive, but the product with negative 3 is not. And so if I have a negative number here, there's no way I get an absolute value less than it, because absolute values are always non-negative. So unfortunately, Carl, surprise, surprise, is wrong again. Okay, let's move on to problem 19. Okay, problem 19, we've got more limits to compute. So we're going to find the limits of these sequences, assuming they exist. And if not, we'll figure out why they don't. All right, now this first one, this is a tricky one. Why do I give it? Because I know you see that alternator, the -1 to the n, you go, hey, look at that, it's alternating positive and negatives. There's no way it can possibly converge. And yet that's exactly what it's going to do. So consider what's happening, right? Forget the -1 to the n. What's happening with this sequence? Well, you have an n cubed as the highest degree in the numerator and an n to the 4th as the highest degree in the denominator. And so you should be thinking, this is basically 1 over n. Yeah, okay, there's a 4 over 7 here, but that's really irrelevant. So this is essentially 1 over n, which we know is going to go to 0. And hitting something going to 0 by an alternator isn't going to matter. Okay, how do we make this precise? Well, let's look at the absolute value of d. Okay, so this is the sequence that we get by just taking the absolute value of everything. And if we do that, all it's going to do really, like from our point of view, is going to kill this alternator. Okay, maybe it messes with some stuff a little bit, but nothing too shabby. Okay, so this is actually just going to be the sequence that contains elements of the form, okay, we take the absolute value of 4n cubed plus 6n minus 1 over 7n to the fourth plus 9n plus 2. Okay, so that's our sequence. And if I factor out an n cubed from the top and the bottom, that would get rid of, oh boy, a lot of stuff. And if I got rid of, oh my goodness, well, what if I even got rid of an n to the fourth? Ooh, that would be fun. Let's try it. So if I factor an n to the fourth out of the top and the bottom, now n is positive, so I can pull that all the way outside of the absolute value. So I'd have n to the fourth over n to the fourth. And what's left over? I'd have 4 over n plus 6 over n squared minus 1 over n to the fourth. Whoops. Nope, we pulled out 4 of them. Whoop, this should be n cubed. Okay, and then what's happening on the bottom? I pulled out n to the fourth. I get 7 plus 9 over n cubed plus 2 over n to the fourth. Okay, of course, these n to the fourths cancel. And then what's going to happen as n goes to infinity? Well, each one of these pieces individually converges. 4 over n converges to 0. 6 over n cubed converges to 0. 1 over n to the fourth converges to 0. 7, of course, converges to 7. 9 over n cubed converges to 0. 2 over n to the fourth converges to 0. So individually, each little piece converges. But if each piece in the numerator converges, then their sum converges. And similarly, the denominator converges. And if both numerator and denominator that converge, then the limit of the quotient will really be the quotient of the limits. So what happens? On the top, this all converges to 0. On the bottom, this all converges to 7 plus 0 plus 0 is 7. And so in total, this is going to converge to 0 over 7, which is 0. So D, absolute value, converges to 0. But we had a result which says if the absolute value converges to 0, then the sequence converges to 0. Okay, if the absolute value is getting very close to 0, then D can't be jumping away. Okay, so there we go. How about part B? Yes. Okay, so I have a sequence E, and I know that a tail converges to 4. All right, well, we have a theorem which tells us that tails detect convergence. Tails detect convergence, which means if a tail converges, then the original sequence has to converge, and it has to converge to the same value. So this implies that E dot converges to 4. Okay, last one. Now we have a sequence F dot, and we know that F dot has a particular subsequence, Fn dot, that diverges. But it has another particular subsequence that converges. So could it be that F dot converges? Well, we have another theorem that tells us that subsequences inherit convergence. Which means that if F dot converged, so would all of its subsequences. So if F dot converges, then so does Fn dot. Okay, so this is important, right? Tails can detect the convergence, subsequences will inherit the convergence. But Fn dot diverges. So F dot cannot converge. So this implies that F dot diverges. So there we go. Okay, so that's all of our sequence questions. All right, let's move on to our next standard and problem number 20. Okay, problem 20, part of the standard on monotone convergence theorem and the Bolzano-Weierstrass theorem. So let's see, we're given a sequence A, it's a real sequence, and oh, it's bounded, okay. And we get to assume that every convergent subsequence of A has the same limit L. And well, let's see, because it's bounded, okay, that's really important because I know, given that it's bounded by the Bolzano-Weierstrass theorem, I know that it has at least one convergent subsequence. And so that convergent subsequence has a limit L, and if I have any other convergent subsequence, it has that same limit L. And we actually are going to prove that A converges. So this would mean if you had some bounded sequence and it doesn't converge, then it must have two convergent subsequences that have different limits. Yeah, so that's kind of interesting. All right, so there's a hint about what we should do here, which is first assume that A doesn't converge. Okay, let's give that a try. So we'll assume A dot diverges. Now, if it diverges, then that means that it is going to get far away from L, right? This same limit L we had here. And by far away, meaning there's some epsilon star where we can't get close, like within epsilon star of L, at least not forever, right? So if A diverges, there exists some epsilon star, some positive real number, such that the L coin, so I'll write down L minus epsilon star, L plus epsilon star, does not contain a tail of A dot. Okay, so if it was the case that A converged, then we would know that every L coin contains a tail. If A doesn't converge, that must mean there must be some L coin that doesn't contain a tail. Whatever that radius is, okay, let's call that epsilon star. All right, fine. Let's see, now what could we do? Well, it tells us construct a subsequence of A dot such that each term in the subsequence is at least epsilon star away. Oh, can we do that? Well, let's see. I might start looking at the terms of A, and I might say, well, okay, do I know that I'm always going to find new elements that aren't in the L coin? Because that's what this is telling me, right? This is telling me that I have some term in A which is not within epsilon star of L. And the fact that I don't have a tail contained in this L coin is exactly telling me that, all right? No matter how far I go out, I'm always going to be able to find terms of A that are outside of this L coin. Okay, so here's what we'll do. We can choose, right? Choose some term of A, and we're going to call it AM1, such that AM1 is not in the L coin. Okay, and this is equivalent to saying that the difference between AM1 and L is at least epsilon star. Okay, so you're outside of this L coin. Okay, so I've chosen that. Now, if I go out further, there must be another term of A, which is also satisfying this exact same property, because again, we know that there's no tail contained in here, right? So next, choose AM2, where M2 is greater than M1. Okay, so I'm really taking a new term in the sequence and it's out past the original one. Okay, such that either way, we could write it this top way or this bottom way. Let me just write the bottom way to stay consistent with the hint. AM2 minus L is at least epsilon star. Okay, and we continue in this way. In this way, oops, this way, to build AM dot. Okay, at each step, I'm going to choose some new term in A, which is not in the L coin of radius epsilon star, which again is possible because this L coin does not contain a tail, right? If at any point you say, no, from now on, everything's in there, well, look, you just found a tail, which is contained in the L coin. Okay, so we build this AM dot. And this AM dot has the property exactly written up above. Okay, so where the difference between any A, M, K, and L is at least epsilon star for all K at least 1. Okay, now it says we're supposed to use Bolzano-Weierstrass to produce a contradiction. Okay, well, how are we going to do that? Well, one thing I do know is this. A dot, the original sequence, is bounded. Now, if I have a bounded sequence, then any subsequence is also bounded. So A dot bounded implies AM dot is bounded. Right? You get rid of some terms. It's not like you can all of a sudden become unbounded. Okay, but once I have a bounded sequence, I can use Bolzano-Weierstrass. I know that AM dot has a convergent subsequence. So by Bolzano-Weierstrass, AM dot has a convergent subsequence. And I don't know, maybe we'll call it AMN dot. Okay, it's getting kind of silly. But in any case, we have this subsequence which converges. Now, it is a subsequence of AM dot, but that also means it's now a subsequence of A. Okay? So AMN dot is a subsequence of AM dot, and hence of A dot. Right? It's just A with, well, even more terms removed. But what was our assumption about A dot? Well, we assumed, of course, it was bounded, but also, we haven't used this yet, every convergent subsequence has the same limit, namely L. But AMN dot is a convergent subsequence. So this implies that AMN dot converges to L. Oh, that's not good at all. If AMN dot converges to L, then that means that every L coin contains a tail. But look at the terms of AMN dot. They all come from, well, this AM dot. And AM dot has the property that if you look at the distance between any term in it and L, it's at least epsilon star. Well, but that means that none of the terms of AM dot, and hence of AMN dot, lie in the L coin of radius epsilon star. So it can't contain a tail, right? So this is a contradiction. This contradicts the fact that L minus epsilon star, L plus epsilon star, this L coin of radius epsilon star, contains, not just doesn't contain a tail, it contains no elements. No elements of AMN dot. That's like the opposite of converging, right? It doesn't contain a tail. It doesn't contain squat. Nothing. Zilch. Nada. Zero. And that's a contradiction, right? Contradiction came from the assumption that A dot diverges. Therefore, A dot actually has to converge. And although we didn't state it here, we even know A dot has to converge to L because, well, if A converges, it is a convergent subsequence of itself. So it would also have to converge to L. Okay, so that's problem 20. Let's go check out problem 21. Okay, problem 21, and oh my goodness, this is a monster problem. Oh my goodness, I bet this must be the hardest problem on the whole test. Okay, take a deep breath. We can do this. Okay, let's try. It says B dot is a decreasing sequence, okay, so it's getting smaller, of non-negative real numbers. Okay, so they're non-negative, but they are getting smaller. And B dot is the sum sequence of B. Okay, that's fine. Now, since B dot has non-negative real numbers, then B dot must be increasing. Okay, fine. Assume that the sequence C dot, oh, there's a third one. Oh my goodness, C dot is equal to, you take the 2 to the nth term of B and multiply it by 2 to the n. Oh my god, what a nutso thing to do. And we're going to assume that it subverges. Okay, so that means that the sum sequence for C dot converges. Oh, and that's what this says. This implies that the sum sequence C dot, which is that, is bounded. Oh, right, because if the sum sequence converges, yes, every convergent sequence is bounded. And it's increasing. Why? Why is it increasing? Oh, right, we knew that the terms from B dot were non-negative. Multiplying by 2 to the n, it's still non-negative. Add them up, yes, it'll be increasing. Okay. Fine. Assume that U is an upper bound for C dot. Well, how do I know it has an upper bound? Oh, right, we said it was bounded. Okay, so it has an upper bound. Call it U. For some positive integer m, there exists a positive integer k such that m is no bigger than 2 to the k plus 1 minus 1. Oh, is that obvious? Like, okay, let me pick an integer. Like, I don't know. What if m was equal to 23? What could that be less than or equal to? Let's see, powers of 2. 2, 4, 8, 16, 32. Ooh, 32, right? This is less than 32 minus 1, which is 2 to the 5th power. 5th is 4 plus 1 minus 1. Yeah, okay. Yeah. All right, I see how you do it. Just make the power of 2 big enough. It'll be bigger than whatever m I choose. Okay, I buy that. Fine. We have that b sub m. Okay, now what? Well, I forgot what b was. B is, it's the sum sequence of the little b's. Okay, fine. And this was an increasing sequence because I have non-negative real numbers. So, if m is less than or equal to 2 to the k plus 1 minus 1, then b sub m will be less than or equal to, well, yeah, this is a bigger index. Okay, fine. Now this was the sum sequence, and so it's just me adding up the first 2 to the k plus 1 minus 1 terms, which are, well, there they are. But they've grouped them in a funny way. Let's see. There's one of them, then 2 of them, then 4 of them. They must be doing like powers of 2. And, yes, okay. Yep, I see that. This is like 2 to the k of them. Then what happened? Is it the same thing? Oh, no, look, they changed it, right? So B3 turned into B2. They're saying it's getting bigger. Why is it getting bigger? Because B is decreasing. So yes, so B3 is smaller than B2. Okay, and what did they do over here? That B4 is the same, but B5 is not B4. They made it smaller number, but that means it's a bigger amount because B was decreasing. Okay, so each one of these, right, is less than or equal to. Okay, yeah. Okay, so everything, they just term by term, they're saying, hey, look, I can make it less than or equal to something. And then, but these are all the same thing, right? So there's 1B1, there's 2B2s, there's 4B4s, there's 2 to the k b, 2 to the k's. That's what they're getting here. And that's equal to ck. I don't remember what c is. C dot, that's the sum of all things of the form 2 to the n b 2 to the n. And okay, so if I did ck, this would sum up everything stopping at, yes, 2 to the k, b 2 to the k. Okay, I believe this. And that's less than or equal to u. U is an upper bound. Oh, for the entire sum sequence. So if this is just some part of it, yep. And there's no negatives or anything. So yeah, so this will be less than or equal to u. Okay. So in total, we've gotten that the mth term of b is actually bounded by u. Oh, so every term in b is bounded by u. I think this means, right? This tells me that b dot is upper bounded by u. Okay, and we want to know why B converges. Well, if it's upper bounded and wait a second, it's increasing though, because look, it's a bunch of non-negative real numbers, right, that you're adding together to get B. So and is increasing mono, right, or is it, which means it's monotone, since B dot is greater than or equal to 0. And look, if I have an upper bounded increasing sequence, I'm just done, right? This implies by the monotone convergence theorem that B dot converges. Like, that's the whole thing, right? Oh my gosh, we had to read all that, and then it just turns out it's just the monotone convergence theorem. B is upper bounded by U, and it's increasing, so it converges. Wow, that was a lot. Okay, let's move on then to problem 22. Okay, so 22, this is a nice, easy refresher question. All we have to do is state these theorems. So let's handle it, right? So MCT, monotone convergence theorem, we just did that one, so this should be okay. Every, how about we'll do the increasing version, right? So every increasing upper bounded sequence converges. Hey, that's pretty good, right? If it was decreasing, then we would want to look at lower bounded, right? Okay. How about Bolzano-Weierstrass? So Bolzano-Weierstrass tells us that every bounded sequence has a convergent subsequence. So of course that bounded is really important here. Oop, we missed sub. Let's move that over. Yeah, if you don't have the bounded, then you can have a sequence like 1, 2, 3, etc. And there's no subsequence of that that'll converge. But once you have bounded, you will get a convergent subsequence. Okay, that was so much nicer. Why don't we move on to problem number 23 and our next standard. Okay, we move on to the Cauchy sequence standard, and we're going to prove that the Cauchy sequence, that every Cauchy sequence that is bounded. Now, one way that you might have thought to do is, well, it's a Cauchy sequence, so we know it converges, and every Cauchy sequence, or rather every convergent sequence is bounded. But we don't want to use that, right? It says it right here, without using the fact that every Cauchy sequence converges. Okay, we're going to prove every Cauchy sequence is bounded. Fine. Well, what does it mean to be a Cauchy sequence? Okay, so if I have some sequence A, it's going to be a Cauchy sequence, and it doesn't. I'm not writing here the rationals or the reals as a subscript just because, well, we're not really talking about it specifically, but it could be the reals if we wanted. All right, right? It doesn't matter. The same argument's going to work either way. Okay, so I have a Cauchy sequence. I want to show that it's bounded. And what does it mean to be a Cauchy sequence? This means for all epsilon greater than 0, there exists an n of epsilon, which is also greater than 0, right? So this is some positive integer, such that if I go out past this eventually number, so if I have m and n both greater than or equal to this n of epsilon, then the m term and the n term of the sequence A are within epsilon. Okay, so this is what it means. You go out far enough and the differences between elements gets really small. All right, so how do I use this to get that it's bounded? Well, intuitively, you should be thinking, well, if I go out far enough, these things are really close to each other, so they can't be blowing up. And then, well, that's if I go out far enough, then there's also the head, that's before I went out far enough, and there's only a finite number of those, so it has a maximum, and that's why the Cauchy sequence should be bounded. Okay, so let's make this precise. So the way I'm going to do this is, since I know I get to get this inequality starting at n of epsilon, I'm just going to compare everything past n of epsilon with a sub n of epsilon. All right. So we have the following. If I consider for, let's say, m at least n of epsilon, then the absolute value of a sub m, okay, I'd like to put an upper bound on this. I know that this is equal to the absolute value of a sub m minus a n of epsilon plus a n of epsilon. Of course, I'll add some parentheses, and now I can use the triangle inequality. All right, when I use the triangle inequality, I know this is bounded by the difference between am minus a n of epsilon plus the absolute value of a n of epsilon. Okay, now I know that since m is at least n of epsilon, and of course n of epsilon is at least n of epsilon, I have a Cauchy sequence, so I get that these two terms are close to each other. So this is going to be less than epsilon plus the absolute value of a n of epsilon. And so what this shows me is that when I go into a tail, namely the tail starting at a n of epsilon, every term in the sequence is bounded by this epsilon that we've chosen and this absolute value of a of n of epsilon. All right. Okay, so does that tell me that the sequence is bounded? Well, almost. Let's do a couple of things to clean this up. First, this epsilon is not something we really can control, so why don't we replace it with a specific epsilon? Because then we'll know, okay, in a specific tail, right, we actually have this number controlled, we know what this number is, etc. So let's say epsilon equal 1. So now we have that the absolute value of am is less than 1 plus the absolute value of a n of 1. Okay, so this is some specific now term. It doesn't change, right, with epsilon because there's just one epsilon. So this is just some specific number, and we know, right, as long as the m we choose is at least n of 1, whatever that term in the sequence is, now we have this. Now, again, this is only for the tail. We still need to make sure that the sequence is bounded in the head. But because it's finite in the head, that's not a problem. So here's how we're going to build our upper bound, right, on the absolute value, really. So let's let u equal the maximum of, okay, let's start with this number here, 1 plus the absolute value of a n of 1. So we know that in a tail, everything in the sequence is going to be less than this number. Okay, what about the head? Well, there's not that much of a head, right? You get a1, a2, and so forth, up through a n of 1 minus 1. So now you have a bunch of elements. Now, of course, some of these could be positive, some could be negative, and since I'm taking the max here, I really need to take the absolute value, because if I'm trying to build a bound around the entire thing, right? Imagine here's 0 and I have some small points over here and then some really big negative ones. I need the bound to go around everything. So I'm going to take the absolute value of all of these terms to ensure I don't get any weirdness with negatives being very, very negative. Okay, so I take the u to be the max of all of these, and now I know everything in the head will be bounded by this bit. So this bounds the head of A, and this we already showed bounds the n of 1 tail of A. And so in total, between all of these, you've bounded everything since we're taking the max. Thus, absolute value of A dot is bounded by u. Okay, and that finishes the proof. Okay, let's move on to problem 24. Okay, so in problem 24, we're given a bunch of statements, and we want to know which of them is true. So let's see here. The first one, every convergent Q sequence is a Cauchy sequence. Yeah, in fact, problem 23 talked about, well, we know that every Cauchy sequence converges. The converse is also true. Every convergent sequence is a Cauchy sequence. So this is a true statement. All right, next, every Cauchy Q sequence converges to an element of Q. So this is a false statement, right? We had our entire section on how we built the real numbers. And the way we built them was by saying, well, we have Cauchy Q sequences, things like 1, 1.4, 1.41, 1.414, etc., which we established converged to the square root of 2, which was not a rational number. So this is a false statement, right? It is exactly this incompleteness of the rationals that gives rise to the real numbers. All right, C, every real number is the limit of a Cauchy Q sequence. Yes, that's exactly what we did when we built the real numbers. The real numbers really were limits of Cauchy sequences. Well, okay, if we were being really technical, we say, right, they're equivalence classes of Cauchy Q sequences. But this is essentially how we're building the real numbers. So this is true. Okay, and then finally, D. There exist Cauchy R sequences that do not converge to elements of R, hence the need for complex numbers. So this was something we had to address in class, which is no, in fact, because the real numbers are complete, that means when you look at the Cauchy R sequences, you don't get anything new. They all converge again to things in R. All right, so there we go. Let's move on to a new standard and problem 25. Okay, so in problem 25, we're moving into the infinite series problems, and we're going to assume we have a sequence, A dot, that subverges absolutely. So remember, this means that if I look at the sum sequence obtained by taking the absolute value of A, that this sequence converges. Okay, the Cauchy criterion for series implies that for every zero coin, negative epsilon to epsilon, there exists an n of epsilon positive such that, okay, if we go into that tail, then the sum of the absolute values of the terms of A starting past m but all the way up through n lies in this zero coin of radius epsilon. Okay, so that's what Cauchy criterion gives us. Use this to prove that the sum sequence for A dot is a Cauchy sequence, and hence that A dot subverges. Well, let's handle this hence part first. We know that if we have a Cauchy sequence, then the sequence converges. So if we knew this was true, right? So if the sum sequence for A dot is Cauchy, that implies that the sum sequence converges. And this is just the definition of saying that A subverges. Okay, so remember, subverges means that the sum sequence converges. Okay, so this is really the key thing here, right? That's what we need to show. So what does it mean for a sequence to be Cauchy? Well, let's see. So let's let epsilon be greater than 0, right? So we've seen in previous problem what it actually means to be Cauchy, but let's actually prove this is Cauchy. So let epsilon be greater than 0. We need to show that if we go out far enough, then all of the terms are near each other. All right. Now, given this epsilon, right? Well, up here we knew for every 0 coin, that's with an epsilon. So for every epsilon, there exists an n of epsilon. All right, this is going to be some positive integer, such that if n is greater than m is at least n of epsilon, then, well, we have this condition here, right? Absolute value of a m plus 1 plus ... absolute value of a n is going to be in the 0 coin of radius epsilon, right? Of course, this is equivalent to saying that the difference between this number and 0 is less than epsilon, or that the absolute value of this sum is less than epsilon. Of course, that absolute value doesn't do a whole lot. Okay, now, what is it we need? Well, if we want to show we have a Cauchy sequence given by this sum sequence, we would need to show that if I looked at the sequence A dot and I went and I looked at the nth term, or maybe the nth term, whatever, and I subtract the nth term of this sum sequence, that this is less than epsilon, right? So this is what we want, okay, for large enough m and n. All right, now, if m is equal to n, no matter what m and n are, if m is equal to n, then of course this is just 0. So if m equals n, then the difference is 0. And there's nothing to worry about. 0 is definitely less than epsilon. If m and n are not equal to each other, then one of them is bigger. All right, so without loss of generality, we assume that m is less than n, or n is greater than m. Okay, in this case, when I look at this difference now, maybe I will put the n first, yeah, just so that we don't have to switch order. Fine, I'll put the n first. So this difference, well, what does this mean? It means I add up the first n terms of A, and then I subtract the first m terms of A. And so what I'm left with are all of the terms from m plus 1 through n. Okay, but now I can use the triangle inequality. And by the triangle inequality, this is less than or equal to the sum of the absolute values. But we know that that sum lies between negative epsilon, and hence is less than epsilon. And so what we've established is, as long as we're, following this, which means that how big does m and n have to be, right? Well, so here, this is for all n greater than m greater than or equal to this n of epsilon that we had up above. Okay, but there we go. So we've just shown that the sum sequence is Cauchy. There we go, and hence A dot subverges. So unsurprisingly, if you have a sequence that subverges absolutely, then it also subverges. Okay, but okay, that's like a big test, right? That's the absolute convergence test. All right, let's move on to problem 26. So in problem 26, we are given 3 statements and we have to determine which of them are false. And if they are false, we have to give counterexamples. All right, well, hopefully not too many of them are false. Let's see. First one, every convergent sequence subverges. All right, this one's definitely false. Most people remembered this. I was so pleased. All right, so we could take, for example, the harmonic sequence. This is a convergent sequence, converges to 0. However, the sum sequence diverges. Okay, this is the harmonic. All right, so this one is definitely false. All right, the next one. If you have 2 sequences, A and B, such that term by term, sequence A is bounded by sequence B, and if we know that B subverges, then A subverges. Yeah, this sounds a lot like the comparison test, but there's this little problem. The comparison test assumes that each of the sequences you're dealing with is non-negative. And we haven't assumed that these things are non-negative. So in fact, let me see, what if I let my B just be the 0 sequence? This certainly subverges, right? It converges to 0. But if you add them all together, you're still just getting 0. And then if I let my A equal the sequence negative n, well, this sequence doesn't even converge, much less subverge, right? So this diverges and disubverges. And the reason this can happen is because you don't have that 0 from beneath bounding A in between something which is converging, right? If you think in terms of the squeeze theorem, right, then when you take the sum sequence for B, that converges. You take the the zero sequence below that converges, right? And so, well, this doesn't tell you what A actually converges to, so it's not as powerful as the squeeze theorem. It does tell you, well, it can't blow up too much, all right? And if this was just sequences, we couldn't say that it converged, but some sequences, because of the nature of the original sequence having to converge to zero, that's enough to tell us that A converges if it's bounded above and below. Okay, but in this case, we don't have that bottom bound, that lower bound. So this is false. Okay, last one. If C and D are real sequences, then the limit of the series sum, right? So we're taking the series of a sum of sequences is the sum of the sequence. Okay, yeah, we're basically saying if I take a series that consists of a sum of two sequences, can I break it apart and evaluate the limits separately? And that's one of our limit laws, right? It says we can do that. Oh, but there's a hypothesis, and we always check the hypotheses. And the hypothesis is that each of these limits individually would have to exist. And we haven't assumed that here. So is there an example we could write down where this limit, say, is going to exist and these ones don't? And the answer is, of course, yes. Because what I could do, I could take C dot to be the sequence n. And of course, this doesn't converge at all. So it definitely disumverges. And then I could let D be the negative of n, right? This is just negative of C dot. This also disumverges. But if I add them together, I get the zero sequence. And the zero sequence definitely subverges. In fact, it subverges to zero. So this is an example where the limit of the sum is not the sum of the limits because the individual limits don't even exist. So this one, regrettably, is also false. Okay, let's move on to a new standard, problem number 27. Okay, problem 27, new standard. We're looking at open and closed subsets. And the problem is to prove that the union of any collection of open sets is open. All right, so we play this game where we're going to take a collection and we need to index it properly, right? We're not going to assume that there's two open sets or n open sets or even a countable number of open sets. Okay, so we're going to say let I be an indexing set. Okay, and that is code to just say, well, this is any size set, right? Like we don't even know, it could be bigger than the size of the reals. We just don't care. So I is an indexing set, and let O alpha, where alpha runs through the elements of I, be a collection, right, or set of open sets. All right, so that means that each one of these O alphas is an open set. Okay, and we want to prove that the union of all the O alphas is open. That's the most general situation that we can get. So we need to prove that the union as alpha runs through I of O alpha is open. All right, well, what does it mean to be open? All right, so a set U is open if every U in U is an interior point, i.e., if there exists some epsilon greater than 0 such that the U coin of radius epsilon is contained in U. All right. Okay, fine. That's what we need to do, only now we need to do it for this big union. So since the condition is every U in U, blah, 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 I need to take some U in U. In this case, my U is the union. So I'm going to let U be an element of the union. And I need to show that there is a U coin inside the union. Right. Well, but if I'm in the union, that means that I'm in one of these open sets, right? So there exists some beta in I. Notice I'm not using alpha because that's my generic variable. There's some beta in I such that U is in O beta. If you're in the union, you're in at least one of the sets. Okay, so U is in O beta, but O beta is open. Well, if O beta is open, then we know that it contains a U coin. So this implies there exists some epsilon greater than 0, such that U minus epsilon, U plus epsilon is contained in O beta. But O beta is contained in the union, right? It's a subset of the union of the O alphas. And therefore, the union of the O alphas contains a U coin. And that's it. This implies that U is an interior point of the union of the O alphas. Okay, but we chose some arbitrary point, so every point is interior. And so we know that the union of the O alphas is open. Okay, that's the proof. All right, let's move on to problem number 28. All right, in problem number 28, we're asked to use complements and the previous problem to prove that the intersection of any collection of closed sets is closed. All right, well, let's take a collection of closed sets. So how about we use C for closed. C alpha, alpha and I. Okay, again, we'll let I be an indexing set. Let I be an indexing set. And we'll let this be a collection of closed sets. All right, and we want to prove that if we take the intersection of all the C alphas, that this is closed. So prove this intersection is closed. Okay, now it tells us very helpfully that we should be using complements. Okay, and the key idea is that a set S is closed if and only if the complement is open. So instead of having to show that this intersection is closed, I could instead show that the complement of the intersection is open. So let's try that. So if I take the intersection and I take the complement of that set, well, by De Morgan's law, which we actually showed a special case way back at the very beginning, where we were looking at, well, in this case, the complement of a union, but if you just flip this, right, the complement of an intersection will be the union of the complements. So here we go. The complement of the intersection is going to be the union of the complements. Now, each one of these C alphas is assumed to be closed, which means that when I take the complement, I get an open set. And so I now have a union of open sets. And by the previous problem, we know that the union of open sets is open. So this uses the previous problem. Okay, so we've just shown that the complement of our intersection is open, and therefore, if I don't take the complement, I must be getting a closed set. And there we go. That's the end of the proof. All right, let's move on to problem number 29. Now, problem number 29 is a bit of a bonus here because the actual problem from the exam, there was a small typo that, well, frankly, made it impossible to solve. So here is a rewritten version that doesn't have the typo, and it is possible. So the question is to give an example of a subset of the real numbers and a real number A that simultaneously satisfies, well, first, the set should be closed, the element should be in the set, and it shouldn't be a limit point, right? So that's what we're trying to do. And so an easy way to do this is let's take a closed interval. Okay, so we just pick something, I don't know, 1 to 4. Okay, this is definitely a closed set. And every point inside the set is a limit point, right? So that would fail C if I just stopped right here. But what if I just include one extra point? Okay, so sometimes called an isolated point. So this entire collection is going to be my S. We know that a singleton point is closed. All right, so the closed set 1, 4 and the singleton set 6 are both closed. Okay, and if I take a finite union of closed sets, that is still a closed set. Of course, the number 6 is in the set, but I claim that 6 is not a limit point of the set. And visually, that's very easy to see, right? So 6 is in our set S, and 6 is not a limit point. Visually, you just say, well, because look, you cannot build a sequence of points that converges to 6, right? Another way to put it is, if you're a limit point, then any 6 coin, right? If 6 was a limit point, then any 6 coin would have to contain elements of S that are not equal to 6. Well, I can easily put down a coin, say of radius 1, that contains only the number 6 from S, right? So if this was 7 and 5, this interval, 5, 7, if I get rid of 6, it does not intersect S. So this implies 6 is not a limit point of S. And there we go. We've got a point in a closed set, which is not a limit point. All right, let's check out problem number 30. Okay, in problem number 30, we're asked to give examples, more examples of sets, or say that it's impossible. So let's see. Part A, an open set that is not an interval. So an easy way to do this, well, let's take an open set. How about 1, 3? That is an interval. But what if I take another one? I don't know, 7, 9. That's also an interval. If I union them together, that's an open set, but not an interval. Okay, now I should mention here, a lot of people wrote down the empty set, which is an open set, and the real numbers, which is also an open set. However, both of these are considered intervals. And I'll see if I can make a video where I talk about why, but both of these are intervals. So they would not qualify for this problem. All right, what about B? A closed set that has no boundary points. All right. Now this feels wrong because what is a closed set? It's one that contains all of its boundary points. But there's a little gray area there. All right. If you don't have any boundary points, then you vacuously contain all of your boundary points. So it's not wrong if we say, oh yeah, a closed set might not have any boundary points, right? That's okay. So it's not so easy for that to happen. In fact, probably about the easiest one you can think of here is actually to take the set of real numbers, right? You could also do the empty set. Both of these are closed sets, and they have no boundary points. All right, finally, the open set, or an open set that has no limit points. Okay. So typically, if we're dealing with intervals, every point inside of them is a limit point. So it's really hard to be an open set that doesn't have limit points, especially in the real numbers where essentially all the open sets just look like intervals. But there's this one interval, bingo, the empty set. It has no limit points, right? In fact, that's about the best we can do. All right. If we just had a non-empty open set that has no limit points, then this would be impossible, right? In fact, so let's write that down, right? If I had O non-empty and open, then I claim this implies that the set of limit points is not the empty set. And the reason why is if X is in O, which exists, right? There is some X because O is non-empty. Then O contains an X coin, right? Because X is an interior point because O is open. But if you contain an X coin, well, every point in the X coin will be a limit point. Every point in the X coin is a limit point of O. So if we had put non-empty here, the answer just would have been impossible. leaving it just as is, the empty set is the only one. All right, let's move on to problem number 31 and a new standard. All right, problem 31, our final standard, define and prove properties of compact subsets of R. In this problem, we're given a subset S of R, and we're going to prove that if every S sequence has a subsequence that converges, hey, that sounds like Bolzano Weierstrass. If every S sequence has a subsequence that converges in S, right? So it's not just converging to something, right? It's actually converging to an element in S, then S is compact. Okay. Well, let's give it a try. So what does it mean for S to be compact? S is compact, well, S is closed, and S is bounded. All right, so we got two things that we need to show. So how about we show that it's closed first? Okay, let's see. Well, what does it mean that S is closed? Well, one way we could do closure is S is closed if S contains all of its limit points. All right, so this is equivalent to saying that every limit point of S is contained in S. Hey, for every limit point, the limit point is in S. That means our first line needs to be choose a limit point, right? So when we start our proof, let A be a limit point of S. Okay, what does it mean that A is a limit point? If A is a limit point, then we know that there is an S not equal to A sequence that converges to A. All right, so there exists, we'll call it A dot. This is going to be an S not equal to A sequence such that A dot converges to little a. Okay, so I have, it's an S not equal to A sequence, but that's actually an S sequence, right? So by assumption, A dot has a subsequence that converges to something in S. Well, that's great because A itself converges to something, and subsequence convergence is inherited from the original sequence. So A dot has a subsequence that converges in S, but A dot itself converges, which implies in fact, it converges to A, right? So it converges to A. That means every subsequence converges to A, because subsequences inherit convergence. Okay, so we conclude that A must be an S because, hey, we have a subsequence that converges in S, and it can only converge to A, so A must be an S. Hey, look at that. We took a limit point, we showed it was an S, we conclude S is closed. Hey, we're halfway there. All right, next we need to show that S is bounded. And this is a little bit tricky to show directly, so instead we're going to do this by contradiction. So we're going to assume S is not bounded. And that's going to give us something to work with. So because S is not bounded, we know I can find elements as big as I like. All right, so let's write that down. So since S is not bounded, for all positive integers n, there exists some element in S which is greater than n. All right, so I can write this as like a sub n, right? There exists a sub n in S such that a sub n is greater than n, or at least an absolute value, right? Like that would be fine. So the absolute value is greater than n. So I can just keep on finding bigger and bigger elements of S. In fact, I can do this in such a way that I get a sequence, right? So for each n, right, I'm getting one. So define A dot just equal to, well, this an that we're building, where we'll start, when n is at least 1. Okay, and everything in here is an element of S, and we know each of these is at least an absolute value bigger than the index n. Okay, so this is an S sequence. Okay, now what was our assumption again? We have an S sequence. We know it has a subsequence that converges in S. So A dot has a subsequence that converges in S. Well, I mean, forget about the NS for a second. We're supposed to get a subsequence that converges. Now, if we write this down, we know the absolute value of A1 is greater than 1. The absolute value of A2 is greater than 2. The absolute value of A3 is greater than 3, etc. The absolute value of A100 is greater than 100. The idea that this sequence A is going to have a subsequence that converges is pretty laughable, right? Okay, let's make it precise. So let's say this subsequence is called AM dot. All right. So if it converges in S, right? So assume AM dot converges to some L. Well, it's a convergent sequence. That means it's bounded, right? So this would imply that AM dot is bounded, because we know all convergent sequences are bounded. But this sequence A is not bounded in a very specific way. It just keeps on growing, right? And so there's no way this AM dot is going to be bounded. Okay, how do we see that precisely? Okay, let's see. So if AM dot is bounded, right, what would that mean? That would mean that there exists some M such that every element in AM dot has absolute value less than M. But, well, what if we just looked at the absolute value of, well, we'll do it this way. Let K be a positive integer such that M sub K is greater than M. Okay, we can do that, right? We know that the indices keep growing forever, so we can find an index which is at least M. But then we have that the absolute value of AMK, well, this is going to be greater than the absolute value of AM. But AM has absolute value greater than M. And this contradicts what we wrote immediately above it. All right, so it's just impossible. Where did the contradiction come from? We assumed that S was bounded. So in fact, this contradiction means S is not bounded. So S is bounded, but we already showed that it was closed. And so S is compact. Whew, tough one. All right, let's move on to problem number 32. Okay, this is our final problem of the exam. Last question about compact subsets. Which of the following subsets are always compact? All right, well, this first one is a union of a bunch of intervals. Okay, so let's write this down to see. So like when n is 1, we would get 2, 3. And then when n is 2, we would get 4, 5. And then when n is 3, we would get 6, 7. I'm starting to see the pattern. 8, 9. Whoops, union 10, 11. And this just goes on and on and on. And so I want to know, is this compact? Well, we know compact means closed and bounded, and this is definitely not bounded. This goes on forever, so not compact. Speaking of closed and bounded, that's exactly what B says. So yes, closed and bounded, compact. A subset which has an open cover. Yeah, right, well, this is supposed to make you think of the topological characterization, which is that every open cover has a finite subcover. Well, this is just saying you have an open cover. Well, everything has an open cover, right? R is an open set that contains all the subsets, right? So R covers everything. So not always compact. Mind you, in A, we knew it was not compact. Here, we just know that it's not always compact. Well, you could have compact sets. They have an open cover, too. Finally, the continuous image of a compact subset of R. Yeah, this was one of our big theorems. We knew that if you took the continuous image, right, and when I say that, I mean, say I have a set D, and f is some continuous function, and I look now at the image f of D. Okay, if D is open, f of D may not be open. If D is closed, f of D may not be closed. If D is bounded, f of D may not be bounded. All very, very sad, but compact. D compact, that was the exception. That implies f of D is compact. So in fact, this is true. We do get compactness here. And there we go. Well, we made it. I hope you got a lot out of this. Maybe even you're just picking and choosing stuff or going through it straight from the start to the finish. I hope it's helpful. All right, we will see you all next time.